Hey everyone! Today we're diving into the world of machine learning, and we'll be looking at some cool clustering techniques using a credit card dataset. We're going to explore how machine learning can help us discover patterns in a credit card dataset using k-means clustering, a simple yet powerful algorithm. By the end of this video, you'll know how to clean data, set up the model, train it, and understand the results. I've shared the full notebook on Kaggle. Check the link in the description to follow along. And if you find it helpful, don't forget to upvote. Before we dive into the code, let's briefly discuss what clustering is and how the k-means algorithm works. Clustering is an unsupervised learning technique used to group similar data points together based on their features. It's incredibly useful for discovering inherent groupings in data without predefined labels. K-means is one of the popular methods you can use for clustering. But how does it work? Imagine these data points in 2D space. Our brains can easily detect a pattern in this data. These points are in 3 distinct groups, or as we call them in this video, clusters. But how can we teach our machine to detect these clusters like we do? This is when k-means comes into play. K-means is one of the most popular clustering algorithms in machine learning. Let me show you how it works. First, we should select k random points. We can choose one of our data points, or as I did here, choose totally random coordinates. These points are called centroids. Then we assign each data point to the nearest centroid. This is how we get our first set of clusters. Then we move the centroids to the center of current clusters, which can be found by averaging the coordinates of data points in each group. Then we reassign data points to groups based on their distance to the centroids, and move the centroids according to the average coordinates of the data points in each cluster. Reassign and recompute the centroids. We repeat these 2 steps, and we'll stop when no change in clusters happen anymore. As you can see, we can discover clusters among our data points using the k-means iterative algorithm. Now that we have a basic understanding, let's jump into the coding part. First, let's import all the necessary libraries for this analysis. NumPy will help us handle large arrays and numerical computations efficiently, and Pandas is great for loading, manipulating, and analyzing tabular data. We'll also use Matplotlib and Seaborn for visualizing our data to get better insights. Additionally, we're ignoring warnings. This helps us keep our output clean and focused on important information. You'll see this throughout the notebook. TSNE is a tool for dimensionality reduction, used to visualize high-dimensional data in 2D or 3D. It's especially useful for clustering tasks because it helps us visually confirm if the data points are forming distinct groups. KNN-imputer helps us handle missing data by estimating values based on the nearest neighbors. Instead of simply replacing missing values with the mean, the KNN-imputer looks at the most similar data points and imputes more accurate values. Standard scaler will allow us to scale our features, ensuring they are all on the same scale. This is critical when working with distance-based algorithms like k-means, which we'll discuss later. By scaling the data, we prevent large numbers from dominating the clustering process. PCA is used for dimensionality reduction. By reducing the number of features while retaining most of the variance, PCA makes our clustering model more efficient and accurate, especially when working with high-dimensional data. K-means is the main algorithm we'll use for clustering. K-means assigns data points to clusters based on their similarity, creating groups of customers with similar spending behavior. We'll go over how the algorithm works in detail when we start clustering the data. K-elbow visualizer is a tool that helps us find the optimal number of clusters by using the elbow method. It visualizes how distortion decreases as we increase the number of clusters, making it easier to decide the right number of clusters for our model. Davies, Bolden score, and Silhouette score evaluate the quality of our clustering model. Finally, Silhouette Visualizer is a tool that visually represents how well each point fits into its assigned cluster. We'll use it later to assess how tight and well separated our clusters are. Next, we've loaded our dataset using Pandas. Here we're displaying the first few rows of the dataset. This dataset contains various features related to credit card usage by different customers. For example, balance shows the amount left in customer's account to make purchases, while purchases shows the amount of purchases from the account. Full feature descriptions are in the Kaggle notebook linked in the video description. To To ensure the quality of our analysis, we need to check for missing values in the dataset. If certain features are missing too many values, it can distort our final results. Here's what we found. The minimum payments and credit limit columns have some missing values. Handling these missing values is crucial because they can impact the accuracy of our clustering model. We'll address this issue by imputing missing values in the pre-processing step. Outliers are data points that fall far below or far above the usual range of values. For example, a very high cash advance or an unusually large balance might represent an anomaly that we don't want to affect our clustering. Identifying and handling these outliers is important because they can pull the cluster centroids toward them, leading to poor clustering performance. Here, we use the interquartile range, IQR method, to find outliers for each feature. The output shows the percentage of outliers for each feature, which we'll address in the pre-processing step. Our data pre-processing will involve 4 steps. First step is removing outliers. Second, imputing missing values. Then, scaling the data. Finally, reducing dimensions using PCA. Let's go through each step. Here, we're iterating over each feature and marking outliers as NaN, or missing values, so we can handle them later during the imputation stage. The reason we do this is that outliers can distort our analysis, especially when we're calculating averages or distances between points, as k-means does. The output shows the updated count of missing values after this step. We'll fill these missing values with reasonable estimates using a technique called k-nearest neighbors imputation, which we'll get to next. Now that we've removed outliers, we can fill in the missing values. We're using the KNN imputer, which works by finding the nearest neighbors to a data point and using their values to estimate the missing ones. This method is more sophisticated than simply filling in the mean or median, as it considers the relationship between different features to produce more accurate estimates. For example, if a customer's credit limit is missing, the KNN imputer will look for customers with similar spending patterns and use their values to estimate what the limit should be. As you can see from the output, all missing values have been successfully imputed. Next, we scale the data using standard scaler. This step ensures that all our features are on the same scale, which is particularly important for distance-based algorithms like k-means. Features like balance and credit limit might have much larger values than features like purchases frequency, and without scaling, the algorithm would place more importance on those larger numbers. By scaling everything to have a mean of 0 and a standard deviation of 1, we make sure that every feature has equal influence on the clustering process. The output confirms that our features are now standardized with a mean around 0 and a standard deviation of 1. Before we move on to clustering, we use principal component analysis, PCA, to reduce the dimensionality of our dataset. High-dimensional data can be difficult to work with and can reduce the effectiveness of distance-based algorithms like k-means. With PCA, we're able to reduce the dataset to a smaller number of components while still retaining 90% of the variance in the data. This allows us to work with fewer dimensions, which speeds up our calculations and improves the accuracy of the clustering. Here, you can see a heat map showing the contribution of each original feature to the principal components. This helps us understand which components carry the most significant information. Before we can apply the k-means algorithm, we need to determine how many clusters to use. The elbow method helps us with this decision by plotting the distortion score, or the within-cluster sum of squares, against the number of clusters. In the graph, you'll see a sharp decrease in distortion as we increase the number of clusters, but at some point the improvement levels off. This point is called the elbow, and it represents the optimal number of clusters. In our case, the elbow occurs at 4 clusters, which means we'll use this value for our k-means model. With the optimal number of clusters determined, we train our k-means model. The fit-predict method assigns a cluster label to each data point. We've added these labels to our original and processed data frames for further analysis. Once we've applied the k-means algorithm, we can visualize how our data is divided among the 4 clusters using a pie chart. This chart helps us understand the relative size of each cluster. For instance, if one cluster is significantly larger than the others, it might represent the majority of customers with similar behavior, such as moderate spending habits. On the other hand, smaller clusters might represent niche groups, like customers who frequently take out cash advances. This gives us an initial sense of how our customer base is divided. To evaluate our clustering model, we calculate two important metrics, the Davies-Boulden index and the silhouette score. The Davies-Boulden index measures how similar each cluster is to the most similar cluster. A lower score is better, indicating that clusters are distinct and well separated. A score close to 0 is ideal. The silhouette score measures how well separated each point is from other clusters. The score ranges from -1 to 1, where a score closer to 1 means that the clusters are well defined. In our case, we see that the clusters are reasonably well defined, but there might be some overlap between certain clusters. The silhouette plot is a crucial visual for evaluating the performance of our clustering model. Each bar in the plot represents the silhouette score for a single data point, which ranges from -1 to 1. A score close to 1 indicates that a data point is well matched to its assigned cluster, while a score near 0 means the point is on the boundary between clusters. The vertical dotted red line marks the average silhouette score for all points. Ideally, we want our clusters to have silhouette scores above this line, as it indicates strong separation between the clusters. In this case, you'll notice that most points have scores above the average line, meaning that the clusters are generally well defined. However, some clusters have points with scores closer to 0, suggesting slight overlaps or ambiguous assignments, but overall, our clustering performance is solid. Now, let's interpret our clusters to understand the characteristics of each customer segment. We'll start by plotting the mean values of the principal components for each cluster. This will give us a spider plot. Spider plots are a fantastic way to visualize the differences between clusters across several features simultaneously. The spider plot, or radar chart, shows how each cluster performs relative to the others in terms of the different principal components or original features. In the first spider plot, we're comparing the clusters based on their principal components. These components are the transformed versions of the original features, and they help us understand the variation in the data. Each cluster's performance is plotted on a radial axis, making it easy to compare. For example, you can see which clusters have higher or lower values for PC1, PC2, and so on. In the second spider plot, we switch from principal components to the original features of the data. This helps us interpret the results in a more meaningful way, as we can see how different customer groups behave based on their balance, purchases, cash advance, and other key features. Based on this plot, we can characterize the 4 clusters we have found in our data. Cluster 0. These customers, whom I refer to as dreamers, have the lowest balance but manage to make significant purchases. How? By relying on installment payments. They have low one-off purchases and one-off purchases frequency, meaning they don't make big purchases in one go. Instead, they opt for installments, as seen by their high installments, purchases, installments frequency. Despite not having much money, they find ways to keep spending. Cluster 1. These are the economicals. Their balance is below average, and they don't make many purchases. Both their purchases and purchase frequency are low, indicating a conservative spending style. These customers tend to prioritize saving, treating every penny with caution. Cluster 2. Let's call these customers the bourgeoisie. They have a good income, reflected by their second highest balance, and they love to spend. This group shows the highest purchases frequency, making both one-off purchases and installment-based ones. They seem to be enjoying their financial freedom. Cluster 3. Now, this group is intriguing. I call them the mafia. They have the highest balance but the lowest purchases. Instead of spending directly, they rely heavily on cash advance, withdrawing cash frequently. It's almost like they're using their credit cards as a cash source for something else, and we can only guess why. Maybe they're into some shady business? We'll leave that to your imagination. Now let's visualize the relationship between key features using scatter plots and KDE plots. First, we have a scatter plot that shows the relationship between balance and purchases for each customer. Each point represents a customer, and the color indicates their cluster assignment. From the plot, we can immediately see distinct behaviors. Class 0 are customers that have a low balance but are making a lot of purchases. They seem to be relying on installment payments to keep spending. Class 1 are the conservative spenders, with both low balances and low purchase volumes. Class 2 has high balances and makes a lot of purchases, typical of high-income frequent spenders. Class 3 are customers that have high balances but rarely make purchases, instead relying more on cash advances. Balance versus purchases. KDE plot helps confirm our hypothesis. Class 0 are customers who spend a lot despite having a low balance. Class 1 have a low balance and spend less than others. Class 2 have high balances and make frequent purchases. Class 3 have high balances but don't spend much. Looking at purchases frequency, KDE plot, it's clear that the Mafia, Class 3, and Economicals, Class 1, purchase less frequently compared to Dreamers, Class 0, and Bourgeoisie, Class 2. The higher frequencies for Dreamers and Bourgeoisie indicate that these customers make more frequent transactions. Purchases installments frequency, KDE plot, shows how Dreamers, Class 0, manage to make purchases even with lower balances. They prefer to spread out their payments over time by opting for installment purchases, allowing them to afford items. Alright folks, we've come a long way. Let's do a quick recap of what we've achieved today. We started by exploring a dataset of credit card customers and diving into some heavy-duty pre-processing. We handled missing values, detected outliers, scaled the data, and even threw in a bit of dimensionality reduction magic with PCA to make sure our model stayed sharp. After that, we jumped into the exciting part, clustering with k-means. We used the elbow method to figure out the optimal number of clusters and ran k-means to segment the customers into 4 groups. We didn't stop there, though. We visualized and evaluated our model with metrics like the silhouette score and saw some cool spider plots, scatter plots, and KDE plots to help us better understand each cluster. And let's not forget our colorful cast of characters. We have the Dreamers, making big dreams happen on small budgets with their trusty installment purchases. Then there's the Economicals, keeping their wallets tightly zipped and pinching every penny. The Bourgeoisie are out there living their best lives, splurging with both one-off purchases and installments, because why not? And finally, the mysterious Mafia, who've got money but don't seem to want to spend it, except when it's for a sneaky cash advance. Should we be worried? Maybe. Should we call the cops? Maybe next time. So, what does all this mean? Well, banks and credit card companies can use this information to tailor their services and marketing strategies to each group. Maybe Dreamers could get special installment offers, while the Mafia, well, maybe we'll just leave them to their cash advances. All in all, we've shown how clustering can be a powerful tool for making sense of large data sets and identifying customer behavior patterns. If you enjoyed this video, don't forget to upvote the Kaggle notebook I've linked in the description below. It really helps. Thanks for joining me on this clustering journey. And remember, data science is like pizza. Even when it's bad, it's still pretty good.
Thanks for watching. I hope you find this video educational and informative. If you like this video, please subscribe to my channel. See you in the next video.